thanks for the introduction. And it was really great seeing Ben because my previous work a decade ago was humanoids. And you probably realize humanoids look really realistic, almost to the level of creepiness. But if you have too many Wi-Fi's going on, too many internets firing up, they are not as smart as they can potentially be. So my work evolves around how do you make embedded, these smart, intelligent robotic systems that do not necessarily have to look like robots, but somehow become more interactive so that it could do stuff that we are not quite sure what's going on in the situations like this. So when you're about to design a robot, we are talking about AI here, we are talking about different forms of robots, humanoids and what's so not. But when you're designing a robot from 20 years ago to now, what has changed? We're still same human, we still have our average height, average speed. The task has changed. We're completely happy when our robots were able to build our cars cheaper because they're faster, stronger, and more precise. We now want robots to do more. It's not enough they do building things faster, but we want them to come to this place, which was never thought possible a decade ago. What are the things we have to consider when we were to bring robots in spaces like this? Well, we need robots to have a higher interactivity, regardless of the situation. We want them to coexist with us. And that's never really programmable because we don't know how many of us are going to be there, where we are going to be, what they're asking us to do. So in the world where things are a lot more chaotic, when we're designing robots, whether we are using how much of AI or not, we need them to stay safer by being more adaptable to this random and chaotic world. How do we do it? Well, we get a lot of inspirations from paper folding art origami. You probably know it's very unproposing, very simple concept of paper folding. Think about this. You have a single piece of paper. You can fold it any way you want. Once you fold up paper airplane, and if you have a little more time and more dexterity, you can build paper cranes. Imagine if you have automatically foldable robotic system that can change its form depending on its environment. Form follows function, function follows form. Traditionally, robots were built to do very, very specific tasks. That defined its form, how heavy they are, how fast they are. That's why when they're confronted with a hole in the wall, mission fails. You can no longer move forward. If you were to have this type of automated system that can reconfigure its form depending on its function, what do we need to achieve? The challenges are how do we embed most essential robotic components on the body? AI, where is this going to work? Microsystem, microcontrollers, motors, sensors, body, circuits. If they can all be embedded into a seamless body all together, and if you were to be able to activate different folding elements as you wish, you can have a folding body robot that can transform its body depending on its task. And that's what we've done with Tribot. Tribot is one of our earlier models of a folding robot. So what you see on the top left is how it's built. Completely 2D. It self-transforms into 3D structure. And once it transforms its body to 3D structure, now it's able to crawl forward. Not that elegant. Some very basic insects do this, but it's an example of how you can give moving capacity to a very simple robot. But if with the same robot, if you were to place it on the carpet, you would not expect it to move forward because the friction of the body changes. What do you do? Normally, the mission fails. But if you're able to reconfigure how its body moves, you can make it hop and roll around the more gravelly street or gravelly road. And then if you have a smaller obstacle that measures about 30% of its body height, you can make it hop it over. The lesson is here that same robot, same body, but because you're able to transform how you're activating different joints, you're able to address different tasks in hand, even if they're to be random and chaotic. So where are we going next? Well, if you were to combine that origami platform with a Lego blocks per se. You can expand its design space. Once you can expand your design space, what can you do? Do more things. So we combine this origami concept with modularity. You're taking the advantage of geometric flexibility of origami robots and functional versatility of modules, like Lego blocks. What does that mean? That means you can let your imagination go wild. Say if you have a triangular blocks that are interconnected, you can make a four-legged robot, and then if you make it flat again and activate different joints, you can do pick and place tasks, traditional industrial application robot. And then if you're a soccer fan, you can have that play soccer during the World Cup period. This was my imagination many, many years ago. Where are we now? Well, you can combine this three-edged robot, all with individual motors, and combine it with passive or active joints. Passive meaning the triangles without motors, active meaning with motors. So what you can see is a very, a basic movement is moving, but what you take on home is with more modules, you're able to create larger design space, meaning larger workspace. If you have a larger workspace, you're able to manipulate different tasks. But what you also take a notice here is not all modules are active. Because they're kinematically linked, there are a couple to move in any way you want. What if these modules can find each other autonomously? And that's what we are able to do now. So Mori 3, now we are in version 3 of Mori, modular origamis, they're able to find each other and link up their joint. Not only they're linked up mechanically, but they are transmitting communication directly through their linked joints. And that allows to do a lot more tasks. Another surprise for Mori 3 is that it's not just an equal length triangle anymore. We can extend the edges as we wish. So not only it's a modules that are homogeneous, but depending on its task, it can become heterogeneous modules with a longer edge on one length and a shorter edge on the other length. What does that allow us to do? Remember that animation I showed you early on with a four-legged robot? We are able to do that. In the animation, we use 12 modules because otherwise it won't walk, even in simulation. Here, you see 1, 2, 3, 4, 5, 6, 12 modules. Oh, the other one had 14 modules. This one, we were able to go with two less modules and able to prop itself up very slowly because we don't want to break all the joints just yet. And it's able to crawl forward. What is so surprising here is that with the same triangle modules, you can do many other tasks as well. Right now, we decide to do a walking forward task. What you don't see here is that normally, if you were to have the same triangular modules, you won't be able to walk forward because you would not have the flexibility in the backbone as you move forward. Here, the edges are extending and contracting as it's moving forward so that it's allowing to have the swing on the legs. We can do a lot more, but I will show you if you're more interested in that after the talk. But I showed you a couple of slides of the robots that are inspired by origami, inspired by Lego blocks. But how can they possibly help us experience our world better? Remotely, closely, if you're having a broken fingers, arms, or have a rolling chair right now, how can it help us to experience the world better? I think we can experience the world better by touching. All of us went through the pandemic. If you were to have another pandemic coming in, would you buy a bigger screen, better speakers? I think what you want to have is the way you can communicate, stay social again. So what we are showing here is that based on the origami robot technology, Alex is pushing onto the thumb button. That gives you not only the ability to pick up objects on screen, but what we see on the screen is a black ball, red ball, and blue ball. It's not exactly the same to Alex. For him, it's a billiard ball, rubber ball, and silicone ball because he's able to feel the texture difference as well as a stiffness difference. This is a way to connect back to the world by touching. It's no longer a virtual reality, but a tangible reality. But if you want to immerse yourself even further, what can you do? Well, you can actually connect this in a series and make a grid out of it. Now you're able to create, well, that was our robot back of the Mercedes-Benz, where we are showing the emotions of the driver to the back drivers where you're not really yelling out the window. And if you combine that with a more practical examples, you can control the surface to move as you wish, depending on the object you're moving back and forth. And imagine these surfaces can react to the force that's coming in, but also recreate the sensation either you see on screen or on the objects that you see elsewhere. So right now, Neil is touching onto one of these modules where he's feeling the different stiffness change, as if he's touching on a marshmallow surface or a billiard ball. And if you want to make it a little smaller, you can make a little push button like so. And push button, and that can be...
Ladies and gentlemen, kindly make your way to the main room. We will begin the program again now.
Well, thanks for staying. So with this small joystick, normally we would go, oh, Jamie, is that a robot? It is a robot, because this device can sense what you're pushing or how you're pushing it, which direction, and gives you back what you see on the screen. It's interacting with you, you being in the loop. You're never outside the loop. You're controlling what's happening. And what does that do? For example, if you're studying your biology class, you're able to feel the difference of the rib cages and the muscle, intercostal muscles. And if you're on top of the heart, you're able to feel the beating of the heart. Currently, we are not adding additional sensory layer for giving you the temperature, but we are also able to change the temperature on the surface. We are also able to give you the texture of the surface as well. So if you're combining texture, stiffness, temperature, you're really having the experience of fully tangible, being a tangible reality. Imagine you can cover up your office like this. Well, you have the different versions of the scales, hand scale for feeling the textures, larger scale for standing on. What could you possibly do if your modules become that big? Well, again, this was during pandemic. I wanted to go skiing or snowboarding. So first, I wanted to control my new snowboard online and see how we will sway on the ski slopes. Mind you, this is not snow. Right now, it's the sand dune. You can change the stiffness of your reactor,
Ladies and
motors.
Please make your way to the main stage. We are beginning the program again now. Thank you.
You can change your stiffness depending on the environment you're imagining. So first, it can be in the sand. You can change to snow, a little bad snow, or a little better powdery snow. And now, you can stand on it as well. So what you're seeing here is Neil's nice socks, as well as the moving platform that's much larger. Currently, we are able to keep up to 75 kilograms a person. The idea is I actually want to ski, so I want to have one under each foot to do the ski motion. What he's feeling is not only the sliding down of the board, but he's also able to brake and feel the bump as it's going up on top of the bumps. So you really can practice on your carving. So thanks for staying. Well, the Reconfigurable robots, I hope I convinced you. You don't necessarily have to look like animal, human, to be interactive with the world. As long as your platform has enough of degrees of freedom and is able to keep you in the loop as it's reacting to the world, I think that is the world where we can have our robots serve better us. Thank you.